energy emitted by the sun. It was quickly recognized in the nuclear reactions leading up to this discovery and subsequent nuclear reactions that a fission chain reaction was possible, releasing a vast amount of energy from a small amount of matter. Fission, as opposed to fusion, is where a large target nucleus is struck with a neutron and splits, releasing other neutrons that can hit other target nuclei, creating a chain reaction. Given a correct geometrical arrangement of radioactive material, scientists saw that a chain reaction was possible. In 1939, American physicists urged Einstein to pen a letter to President Roosevelt detailing these fission studies, writing that it is conceivable that extremely powerful bombs of this type may be constructed. Roosevelt authorized and funded neutron experiments less than 10 days later, which ultimately led to the Manhattan Project. Along with its design potential as a weapon, chain reaction fission was also quickly utilized as a heat source, leading to its ultimate use in nuclear reactors. The legacy of the atomic age is well beyond the scope of my project, but it began with a very simple cosmological inquiry. Moving to spiritual and social effects, the effects of major changes in cosmological models seen here was primarily a rigorous debate among secularism, religion, and philosophy, which led to major changes in human thinking and overall worldview. This is derived primarily from the Copernican revolution and the creation of the Big Bang model. With the introduction of the Copernican model and other observations, cosmology sparked a powerful, volatile idea that the entire universe and its working could be explained with human reason alone. To fully grasp this, we must understand the Aristotelian and Ptolemaic models that preceded Copernicus. The Aristotelian geocentric universe, as conceived by Aristotle in the 3rd century BC, was considered the first great cosmological era. This model was classified as Earth-centered, static, and unchanging throughout eternity. This model was based on the fact that the stars, sun, moon, and planets all appear to revolve around the Earth. It was also based on a common sense assumption that the Earth is stable, massive, heavy, and therefore cannot move. The only plausible explanation left was that the Earth was unmoving and at the center of a celestial sphere. Aristotle asserted that concentric celestial spheres, each of which contained a planet of the solar system, concentrically surrounded the Earth, the third of which contained the Sun, the outermost containing the fixed, immutable stars. This model was the most popular model until 2 AD, when the Ptolemaic model was introduced. The Ptolemaic geocentric model largely mimicked the Aristotelian model, and in many ways can't be considered an entirely independent model. This was detailed by Ptolemy in his work Almagest in the 2nd century AD. It was technically not a new theory, as Aristotle put forth the geocentric model first. Ptolemy utilized the work of previous astronomers, and Almagest is more widely considered a synthesis and confirmation of the then current cosmological beliefs. Ptolemy utilized the previous logic of Aristotle, Pythagoras, Apollonius, and Hipparchus, and it perpetuated the idea of epicycles. To explain the complicated motions of the planets, an epicycle is a small circle in which a planet moves. Each epicycle has at its center point a deferent, and the deferent itself is what moves on an orbit around the Earth. This was the only explanation that Ptolemy could find for the complicated motions of the planet in a geocentric model. Ptolemy gained support from the Church as his placement of mankind at the center of the universe reflected the idea that we are God's creature, and therefore the center of his caring and attention. Accepted for over millennia worldwide by Islamic and Western astronomers alike, the Ptolemaic model was the most successful model in all of history. The Copernican model of 1543, as detailed in On the Revolutions of Celestial Bodies, revisited an ancient Aristotelian argument of the solar system by reasserting the idea of heliocentricity, and succeeded in surpassing the Ptolemaic model. Copernicus revisited and strengthened Aristarchus of Samos' 280 BC arguments to the extent that they gained popularity and observational confirmation amongst astronomers, but at the time this was largely in secret due to pressure from the Roman Catholic Church. The crux to Copernicus' model in gaining initial scientific popularity was the fact that Ptolemy's complicated epicycles were not necessary to explain retrograde motion in a sun-centered solar system. Retrograde motion is the apparent backwards motion of planets across background stars throughout the years. This is an example of the retrograde motion we will see from Mars between 2009 and 2010. As you can see, it moves forward, then appears to move backwards, and continues forward again. To explain retrograde motion, Copernicus had a very easy task. He reasoned that the Earth was closer to the Sun than Mars, and so Earth, being on a smaller, closer orbit, revolved around the Sun faster than Mars. And so as we pass Mars in orbit, we see it going backwards. Ptolemy could only explain it using complicated epicycles, and as Mars goes backwards in its epicycle, is when we see this apparent backwards motion against the background stars. Clearly, Copernicus was much simpler. Work from Galileo, Brahe, and most of all, Johann Kepler provided observational evidence and supporting mathematical theory for a heliocentric model. Kepler predicted the motion of the planets with astonishing accuracy using 3 laws of planetary motion. He pieced together using Copernicus' model and Brahe's data, creating a scientific basis for his model that was beyond reproach. The first law that Kepler discovered was that all planets move in elliptical, non-circular orbits. This fine-tuned accuracy to an unprecedented level. Kepler's second law was that a line joining the Sun and a planet sweeps out an equal amount of area over equal intervals of time. This explains how a planet's speed seems to change, as when it passes closer to the object it orbits, it speeds up. As it passes further away, it slows down. Kepler's third law is the mathematical law, that the square of a planet's period, the time it takes to orbit the Sun, is directly proportional to the cube of the length of its average orbiting distance. This gave a mathematical relationship that aided predictions that is still used today. The next piece came in 1572, when Tycho Brahe observed a distant supernova, something that was conventionally described as a near-Earth phenomenon. But Brahe showed a lack of visible parallax, and thus the supernova was far beyond the moon. To get an example of parallax, everybody hold out your thumb. Now close your right eye and look at your thumb. Then switch between your eyes and watch how your thumb changes in position against the background that you see behind it.
Right on.
Brannon proved the same thing. In showing that the supernova doesn't change its appearance against the background stars, he showed that it wasn't something that was close to the Earth, and that it was, in fact, something just as distant as the background stars. And therefore, the background stars were changing, which challenged the Aristotelian model, which claimed that they were immutable throughout eternity. Lastly, Galileo harnessed the use of his new telescope in the 17th century to provide observational evidence to support both Copernicus and Kepler. Galileo noticed that Venus appeared to change in size, larger as a bulbous shape, smaller as a crescent shape, thus indicating that it demonstrates phases like our own moon, confirming that it orbits the Sun. The only way he could explain this was that the Sun and the Earth were separated, with Venus orbiting the Sun in between. As in opposition, when we see Venus on the far side of the Sun, it appears full. In inferior conjunction, we see it closer to the Earth, and it appears new, as no sunlight is reflecting off of it, confirming that it orbits the Sun and not the Earth. Lastly, upon discovering Jupiter's 4 moons, Galileo provided the first confirmation of Kepler's third law by observing that the square of a moon's orbital period is in fact proportional to the cube of its average orbiting distance. With all this in mind, let's look further into the effects of Copernicus and his findings. Copernicus' radical model, combined with the calculations and observations of Kepler, Galileo, and Brahe, was scientifically confirmed. It was essentially entirely bomb-proof. Copernicus' model so thoroughly challenged the religious and philosophical paradigms of his time that its validity forced society to accept a new confidence in human reason that had not been seen before. Copernicus, in fact, was so concerned about the reactions to his model that he did not publish it until he was on his deathbed. Galileo was placed on house arrest for most of his life for supporting Copernicus, and was even forced to refute his claims in front of the Pope himself. The Ptolemaic Aristotelian-based model was the accepted model of the Roman Catholic Church, and therefore the intellectual world at large. Many felt that Copernicus supposedly challenged God's authority in demonstrating that humanity was capable of an explanation more accurate than the Church. This was because Copernicus' model had a simplicity that surpassed Ptolemy's, thereby falsifying Aristotelian physics coined to by Ptolemy and challenging the Church. In the course of identifying these 3 laws, Kepler made it apparent that mankind could explain celestial physics just as well as Galileo had recently proven we could explain terrestrial physics, proving that celestial physics and terrestrial physics were in fact one and the same.